Hey guys, what's going on? Memes here. Yes, yes. I know it's been a while since I've done this stuff and things. Totally wasted a bunch of time, and occasionally, while going down the random Wolfram or wiki hole or anything, may have discovered something, at least for me, is interesting. Of course, people know about this, but sometimes a different perspective may be useful. I don't know. We're gonna have to see. We're not gonna do any of the little Wolfram stuff intro or anything. We don't need that because we're gonna cover technically a lot pretty quickly. There's a crap ton of links in the doobly doo below. What we're gonna, we'll upload the actual notebook. I was like starting to write a paper and I found more. Okay, we'll just jump into it. Okay, so we've been ranting a long time. Let's embiggen this dude. So how do we do that? Boom, embiggen. Okay, yada yada. Alpha defined structure constant. Why? Why am I speaking any words on here? Okay, it is defined in our standard colloquialness of the science as basically elementary charge squared over 4 pi, speed of light, electric times the electric constant times h bar. Okay, then you get this number over here. It's very pretty. Okay. So I'm looking at that construction. I looked at it before and I kind of got into it. And again, I am a dude on the internet. I do not have any professional background training in physics. I've just been looking at the stuff for a while and occasionally get an itch in my brain. I'm like, why is this the case? I don't know why it's the case. That's why I'm here with you all to try to see if we can't figure this out. Hey, Upcycle. Thank you for joining, my friend. Good to see you. All right. So where are we going? Yes, yes, Jax, here's the thing. There's actually going to be minimal math. A lot of it's just words. You just put the words, you put in some stuff, it gives a thing. That's the beauty of Wolfram Alpha, because we're using Wolfram Alpha because the data on here is actually curated and stuff like that. So there's some things that I may have some disagreements with. We'll delve into that. But okay. So basically, you look at this construction. Okay, let's extend this construction. Where are we going? Hold on. I forgot to hit back tab because I am a bad person, and I read my. Okay, so what the heck is that bottom term? Elementary charge squared. The charge of the electron or proton squared. Okay, cool. Base unit as we define charge. So what's that bottom term? That 4 pi times speed of light times the electric constant times reduced by. See, look, we got the words there. I put in the words because you can do that. So it gives you this number here. I'm like, I don't know what this is. But I look at it, I'm like, wait a second. It's got time squared and current squared. So if there's no standard named unit or interpretation, maybe I could do something. Like Professor Carroll said, take the square root of it. So I did. What do we get? We get this number. Hold on, let me reload because I'm bad. This was a number that looked quite familiar. Why did it look familiar? Scroll down. Wait a second. It appears to be the value of the Planck electric charge. Why? It seems a lot simpler than writing all that, but essentially, it is essentially how we defined it because, hold on. Well, we'll do the quick deviation for this to make any sense. All right. So, hold on. Go to the Planck charge. Here's the reason. It took me a while to actually figure this out. And I was like, oh, duh. Oh, look. 2 times the square root of pi, the square root of c, E naught, the electric constant times h bar. Okay. So if you square that all, you get the other thing. Cool? Groovy. All right. So that got me to thinking. Could we do a little bit more? Okay. So we could shorten that original expression to, rather than all this jazz, which is totally cool, you can do it however you want. But if this is essentially this elementary charge over the Planck charge squared, cool. We're getting the same answer. All right. Hello, Rick. I think you may enjoy this, my friend. Ernesto, good to see you, my friend. Good to see you. I hope all is well. But I think y'all are going to enjoy this. Could be wrong. We continue. All right. So that got me to thinking. All right. So I got this number here. This is a dimensionless constant. Nobody knows where it comes from. So I'm like, wait a second. This is a unit of charge. What if I did another unit of charge? How about the definition of charge? So I replaced E squared with or just E with coulombs. Okay, it gave me this number. It's a dimensionless number. I have no idea what it means. I did, however, notice something. It's to the 35th power. Is there an elementary unit that I know of that is something associated to the 35th power? No. But the Planck length, it's to the negative 35th power. So I'm like, oh, if I multiply it by that, so I got this. Gives me 4.595 meters. That means absolutely nothing to me. If I remove the meter term, though, 4.95 does remind me of something. It reminds me of an inverse. Because if we do a little inversion, wait a second. So I basically just put 1 over that stuff. It gave me the string of digits. I'm like, it's a 0.21764 meters reciprocal. Okay, now I don't know what that means, but those are the digits to the Planck mass. Huh. At least according to Wolfram Alpha. Okay. That's kind of cool. But it's not the right power. Is there something I could potentially multiply it by to get it to the right power? How about Ampere's constant? Okay. Oh, look, it gets it to the right power, but we're still in the wrong dimension. Beams, okay, because our kilograms divided by seconds by amperes. Oh my God, what does that mean? Okay. I didn't spend all the time to figure out what it means. Okay, maybe now at this point I kind of have. So I'm just like, wait a second, what are the dimensions? Time and current. Now, current is always confusing because it's actually a derivative of charge divided by time. Wait a second, charge divided by time? We used charge to get into this. Maybe we can use charge to get out. So I multiplied it by Coulomb squared. Oh, look, 2.1764 times 10 to the negative 8 kilograms, yada, yada, aka the Planck mass. Okay, that's cool. Now, why the heck am I showing you all this and everything? I thought it was kind of neat. I got to it through a back-ended, kind of combobulated way and everything. But yes, the square root of pi. Why is that a thing? Working on it. Some people out there with some very, very interesting ideas. We're gonna see how things pan out. Ernesto, I'm thinking about the question you asked me before. I think it's becoming a lot more relevant, or at least the areas I'm looking, it seems to be bringing me there. We should talk again. Yes, we should just go play some. I have played a lot of, hey, server first level 80 Death Knight, my friend. But okay, why am I showing you all this? This big convoluted thingy. Well, eventually, after writing some things up and looking at it more over the weekend, I'm like, okay, let me simplify it. Okay, so yes, all this different things. Your Warlock will not level its. Hey, I don't even know the current gameplay of Warlocks. I haven't played in a while. All right, so I need to go to yet another window. Where are we going? I believe it's this guy. Is it this guy? No, it is not that guy. I apologize. I'm skipping ahead. All right, so it should be. Is it? Yeah, this window. Okay. All right. So the simpler expression is I just plugged in these things. The Ampere constant, which is coincidentally the Planck mass times the Planck length over the Planck charge squared, or what the minimal arenas model is, basically the inversion boundary. which coincidentally, that without the dimensions goes in to basically be the inversion point for like the 288 constants of nature. Um, it's an interesting thing. Again, very interesting things seem to happen at around 10 to the negative 7. Uh, Inverses are also important because that's basically the whole point. Okay, what the heck is this? I put these things together. What do we get? 3 times 10 to the negative 40 kilogram meters. I have no idea what that means. What does it mean dimension wise? Its interpretation is mass distance because it's mass times length. Okay. Why am I showing you this? Basically, that crazy convoluted thing I showed you before, it simplifies when you just do the Ampere constant times the Planck charge, because the Planck charge is also in the Ampere constant, so of course it comes out to mass and length. Okay. Why am I even showing you this? So think about this. Okay. Because at least I thought it was cool that you put in, again, this was cool to me. Again, the dimensions, it seems to be a duh thing, is if there's a claim of perhaps a very interesting place where maybe things are mixing together, or there's some form of an inversion boundary or something going on. When you put these in here, all right, one of the Planck length, okay, gives us the Planck mass. Cool. What happens when we put in the Planck mass? Oh, duh. Oh, we get out the Planck length. Hold on. Was there something else that I wanted to show here? Okay. Oh, never mind. I was getting ahead of myself. But okay. So you get the Planck length. What happens when we do the Planck time? Oh, look. What the heck is this term over here? 6.525 kilogram meters per second. Only reason that kind of meant anything to me was from Professor Tuft giving a lecture. I think it's this guy. Oh, no, skipping ahead. Oh, forward now. Duh. Oh no, what did I do? Oh. Wow, I'm so bad. All right, we'll do it the easy way. Boom. Spoilers here. Planck momentum. We divided by that. Oh, I totally got that wrong then. Wait, what am I doing? Oh, I'm supposed to multiply by the Planck momentum. I think that's what I did before. Oh, never mind. All right. I obviously have no idea what I'm talking about. Unless I skip ahead. I believe it's the Planck momentum. Hold on. What is the Planck momentum? Oh, it is that. I'm just bad with setting up the brackets. All right. These things happen. This is the right dimensions. Yeah, mass length time. Boom. Back. Mass length time. Cool. All right, moving ahead. What the heck is this? All right, 1 over a Planck electric charge. Boom. Piezoelectric accelerometer voltage sensitivity. I really don't know what that means. That sounds like the precision measurement of a particular piece of equipment. Okay, I didn't delve into that much. Okay, what happens when we add in the speed of light? Oh my god, we get all these things. Oh, that number looks a little familiar, but there does seem to be some deviation. We'll get into that. Oh, just a note, at least according to the minimal arena and the geometric closed forms of the Planck constant, that is calculated according to Wolfram Alpha. I'm pretty sure some other places. There's a deviation from the calculated value that we have and the one that's here. It apparently kicks in at the 7th significant digit. And I may, and again, I'm just putting that out there. Why may we have confidence in our claim? We'll get to that. I'm not saying that perhaps some conventions hold more water than others, but we're going to have to see. Okay, so that's the thing. We're not going to bore you with all that. There's crazy links and stuff there. What happens with speed of light squared, blah, blah, blah. Electric flux. Electric flux. Oh, isn't that what we're kind of supposed to be talking about? All right. What happens if we take that electric flux and we divide it by the Planck magnetic flux? Oh, gee golly. Something that Maxwell discovered a long time ago. Look, you get the speed of light. We just happen to have some more measured digits of precision. Modern technology is freaking amazing. But yeah, no, see, that's the thing, Jax. Depending on how you're looking at it, it is very interesting. Don't worry. We're just going to go through it. All right. So what happens when we do the Planck temperature? The Planck temperature, I ran into a snag because it just didn't work by itself. So we needed to incorporate. Hold on, did I show it here? Yeah, no. Basically, the Planck temperature is calculated. You need to insert Boltzmann's constant. So I needed to insert Boltzmann's constant to do some interesting inversion on it. Which, when we do that thingy there, we get, what is this? 52 seconds squared per meter. Group velocity dispersion with respect to angular frequency. I have no idea what that. Okay, I believe you're talking about an area. No, excuse me. Okay, it's inverse area per time. It sounds like a spherical shell kind of going out to me. That's just my base interpretation. I'm sure I'm wrong. Somebody please correct me. Could I get something else there? Because that is an interesting magnitude, that 10 to the negative 52. Or 10 to the 52, one of those inversions. Actually, the one that I probably recognize more is when we invert our inversion. What happens then? Oh, 5.5607 times 10 to the 51 meters per second squared. Well, that's acceleration. General corresponding quantities. Oh, I've seen these pop up before. Oh, 0.25, 2.255 times 10 to the 31 Kelvin. Well, it's pretty freaking hot. It's basically the under temperature calculation, the Hawking temperature calculation. Essentially, they give you the same values for apparently different reasons. And then the gravitational field. Okay, I looked at that number. I'm like, wait a second. That seems pretty close to the Planck temperature. How do I get there? We'll get there in a second. I'm sorry. All right. So basically, when you take that and you divide by the Planck acceleration, it's 1. Okay. But rather than inverting it, let's just divide up a circle. Well, like I've heard somebody say, we just need to have these circles. Maybe they're ginormous. Oh, look. When we get there. Oh, that seems to be the magnitude of the Planck temperature. Then to the 32, 1.417. We got a lot of gravitational acceleration there. All right. That was cool. And then what is supposed to be the whole dang moral of the story? All right. So if we believe the stuff and thing, I'm getting to a point. Like a lot of this stuff, I'm like, okay, cool. It's a way of thinking about things. It simplifies it a lot for me. Why are you doing this crazy live broadcast at 10 o'clock at night? Okay. I swear there's a moral to the story. But, okay, we look here. So what's the interpretation? You put these magical words into Wolfram Alpha. Unit per constant, Planck charge squared. You throw on your little protective brackets so it doesn't confuzzle each other. You throw the division symbol in there. You do the same brackets for protection. Planck mass and Planck length. Okay. Because that was an expression, that whole Ampere constant times Planck charge squared gives you mass length, mass distance, or mass length of dimensions. So what happens when you multiply the Planck dimensions of mass and length, you get one. Duh. Okay. This is something that we assume to see. All right. We go to the third window here. Oh, okay. That makes sense. All right. Thanks, Rick. Oh, no. Don't get me wrong. No, there's a lot more math. I'm sure there's a lot more math. Again, this is for perspective framing and perhaps totally personally biased reasons. Okay, there are totally biased reasons. So we'll get into that. So Where is my last friend? Oh, our last friend is okay. So we go back to the other dude. That is the one. I think it's this dude. No, that was the last dude. Okay, I'm sorry. All right, we'll just close that. Okay, much simpler. Much simpler. Okay, here we go. All right, so we're back at that last little window there. Okay, our one. Why do I say this? If we believe this is one, if we believe there's some form of unity here, perhaps we could do something interesting. Perhaps we could try to maybe validate calculations that you can claim are true, and maybe they are, but you would need some method of reference. And I'm sure this is a wrong way of doing it, but I'm trying to be less incorrect. So hopefully y'all out there can maybe help me, message me, email me, whatever it is. Okay. So what do I think? Because all right, that's a dimensionless number. So what happens if we do that and we literally just okay, rather than putting the ones, put the units themselves there? Or the units occasionally are defined by some of the other terms, and there's a lot of history there. It's quite fascinating. Okay, so the whole claim is, all right, if we assume that's a one and we put in the units, we can get this dimensionless number here. All right, so I put it in that way, gives me a really small number. Okay, so I put it in the numerator, the kilogram meters, divide by that thingy we were talking about. All right, it gives me a really big number. All right, so we get that really small number. Okay, really small because it's negative 43, really big. All right, so we assume this is one. All right. So we plug the numbers in, and we assume coming together, we get that kind of unification thing. Because like, all right, I toss in the Planck length. It's like, why am I getting the Planck mass or something like? Because these are ones. Cool, and we have high confidence in these to so many significant digits. All right. So what happens when we get this? We get this number right here. That's a lot of zeros, my friend. How many zeros is it? That's approximately 10 zeros. Shout out to the folks at Wolfram Alpha because I'm like the speed of light. It's like they got like 9 significant digits. H bar, they had 12. They cut it off because the error was kind of large. But it's like you got that. You got the electric constant and everything and stuff in there. It's like bravo. They got 10 significant digits. That's about as accurate as you can get for I think the data that you put in there. Okay. So if we believe this to be true, if we believe this to be a one type of thing with this construction, what would happen if we took some calculated terms, let's say that the ones that did geometrically by calculating, taking the numbers we had and then solving for x when setting it to e and then raising it to the, and again, it's a claim. It requires a thoroughly constructed model to help gain confidence in. Is there another way to check? I don't know. But I did that stuff anyway with the calculated values that had. So basically, when we put this in here, and again, we get our deviation ones. 1, 2, 3, 4, 5, 6. Okay, seventh. On the seventh digit here, all right, we get that deviation because that's about. There's a lot of stories we can talk about. We'll talk about them another time. But okay, so we got this thing in here. So we got basically this number. What is this? 1, 2, 3, 4, 5, 6, 7, 8, 9. We got 9 digits there. It gave us like 10 digits of accuracy, so it seems to be very precise. Okay. So we did that guy. Oh, all right. So we get some more digits here. We got 1, 2, 3, 4, 5, 6. It does deviate around 7. Very small, but it does deviate. All right. So was it 7, 8, 9, 10, 11, 12, 13, 14, 15. I may have miscounted there. All right. So we're just doing the same thing. We're just doing the calculated values. All right. What do we get? That's a good deal of zeros, my friends. How many zeros? According to my calculations, or Wolfram Alpha's calculations, 16. So, now, what does this all mean? I don't know. It's the whole claim was maybe it's a way to check for some form of what people may call a unity. I'm saying that in quotations because unity does mean different things depending on the context. But is there a point of what we would, at least within our realm of what we can measure these stuff and things, be a point of union? I don't know. I know I went over a bunch of stuff. It was very quickly. I got all the links that actually allowed me to put that in there, but I'm curious what y'all think. I think it's a very interesting thing, and we'll see where it goes. I'll try to upload the computational notebook probably tomorrow. So, other than that, take care of yourselves. Peace out, everybody. Well, the thing